So today I want to start by talking about the three-sphere recognition algorithm, and in particular how it connects to ideas of geodesics and minimal surfaces. So the problem is that you're given a simplicial complex and you want to say whether a three-dimensional one, you want to say whether it represents a manifold that's homeomorphic to the three-sphere. So this is a problem, it's probably the simplest algorithmic problem for three-dimensional manifolds, and certainly was thought about for some time before it was solved, about in the early 90s. It's equivalent to asking whether the simplicial complex is simply connected, as we now know from Perlman's work. And one of the reasons people were interested in this problem was to try to get try to look for a counterexample to the Poincaré conjecture. In fact, it wasn't even clear whether the Poincaré conjecture was decidable at that time, which now we know that it is. But remember, we still don't know whether the four-dimensional smooth Poincaré conjecture is decidable. So it's not completely ridiculous to think that it might not be. Another place where this three-sphere recognition problem comes up is in trying to determine whether a four-dimensional simplicial complex is a manifold. So if you have a collection of four-dimensional simplices and you want to see if they are glued together in such a way that they make a four-dimensional manifold, you have to check that the link of a vertex, all the three simplices that fit around the vertex, form a three-sphere. And I think that's actually implemented now in Regina. So it's actually being used. Okay, so to understand the idea that led to the solution, let's step back and think about how we'd recognize a two-dimensional sphere. So if we have a two-dimensional complex, simplicial complex, so we have a union of triangles with some of the edges identified in pairs, how can we tell if it's a two-sphere? Well, the simple way is just to check the Euler characteristic. If the surface is connected and its Euler characteristic is 2, then our algorithm will just output yes, and otherwise it will output no. So that's a simple algorithm, but unfortunately that doesn't generalize to higher dimensions. There's no known invariant of three manifolds that distinguishes the sphere from other three manifolds and that is computable. So rather than doing this, we'll try and come up with a different type of algorithm, a harder algorithm for two-dimensional manifolds, but this one will generalize to three dimensions. So what is the idea? The idea is to try and understand this system of geodesics on a two-dimensional manifold. So now we're leaving the world of simplicial complexes and entering the world of Riemannian manifolds. So these are smooth manifolds with Riemannian metrics. And what I've drawn is just some examples of different surfaces and the geodesics that lie on these surfaces. So the idea is we're going to look at a maximal family of disjoint geodesics on a surface. So for example, on a round sphere, that maximal family consists of a single equator. Right? You have a lot of choices as how to pick that equator. There's many different equators. But once you pick one, there isn't any other one that's disjoint from it. On an ellipsoid, you again would have one choice. You could choose one, but then there wouldn't be any others in the complement. But once you start getting away from convex manifolds, convex surfaces, you'll see that there can be many disjoint geodesics. And these come in two flavors. There's the ones that I've labeled blue here, and the ones that I've drawn in red. the ones I've drawn in blue. And the difference is, what's the difference between them? Well, if you think of these surfaces as being, first of all, cover them with butter so everything's very slippery and can move around, and then take a rubber band and try and put it where these geodesics are. If you have one of these blue geodesics and you just touch it a little bit, it'll fly to one side or the other. But if you take one of these red geodesics, they're stable. They won't move. You could push them around and they'll just snap back to where they are. So these red geodesics, these stable geodesics, are locally minimizing, they minimize length in some neighborhood, whereas the red ones, the blue ones don't. They're unstable. So let's look at this a little more. What's the definition of a geodesic? You can define it in various ways, but one way is that if you take any two sufficiently nearby points, the geodesic gives you the shortest curve connecting those 2 points. So even on an equator, if you have 2 points that are close together on the equator, the great circle gives you the shortest path between those 2 points. So that's always true for geodesics. But it's not true once the 2 points start getting far away along the geodesic. So we'll say that a geodesic is stable if there's some neighborhood of it in which the entire geodesic, the entire curve, is the shortest curve. So there's a little annulus surrounding that curve, and the geodesic will be the shortest curve going around that annulus, if it's stable. And otherwise, it's unstable. And there's similar ideas in higher dimensions. If you have a surface in a three-dimensional Riemannian manifold, you can look at its area and compare it to nearby surfaces. Minimal surfaces will be locally area minimizing. So if you take any point and a little disk around that point in a minimal surface, that disk will be the smallest possible, it will have the smallest possible area among all surfaces with that boundary curve. But once you get bigger, you can have unstable minimal surfaces like the equator of a three-sphere, which you can push off to decrease area. So there's some pictures of what these geodesics look like. On the surface of the Earth, we see these when we fly on those airplane maps. The planes try to fly along geodesics, connecting points, stable geodesics usually. On surfaces, a basic lemma that we need to use is that if you take any non-trivial homotopy class, any curve that's not, that you can't shrink to a point, you can always shrink it to a geodesic. It'll always have a geodesic in its homotopy class, and in fact, if you take an embedded curve, the shortest geodesic will also be embedded. And this is true in any metric at all, not just in standard metrics like the hyperbolic metric on the surface, but if you take any metric at all, the shortest geodesics always exist and they're always embedded. Now we're going to use I want to actually state a theorem about these geodesics, so we have to make some assumption about the metric. We want to use a generic metric, and what that means is that you don't have some nasty behavior. For example, in a general smooth metric, you may have a cylinder piece inside a surface where you see a whole family of parallel geodesics. A flat cylinder has infinitely many parallel flat geodesics. So we don't want to have to worry about those. You don't have to make this assumption, but it just makes the argument a lot harder if you have to deal with these cases. The other thing you don't want is you don't want these geodesics that you can decrease area to one side, pushing them to one side, but not to the other side. See, if you have the equator of the Earth, you can decrease its length by pushing it to the southern hemisphere or the northern hemisphere. But you can create these artificial metrics. They're very non-stable, though. If you take a random perturbation of a metric, then you won't see these kinds of behavior. And that's actually a theorem in all dimensions that was proven by Brian White in 1991. It's called a bumpy metric. So what I'm going to do now is show you that if you take a generic metric on a two-sphere, then a maximal family of separating geodesics, a general metric on any surface, not necessarily a two-sphere. If you take any surface at all, the surface on the right is a torus and on the left is a two-sphere. If you take any metric at all on a surface, you'll find that a maximal family of separating two spheres has the following properties. First, if F is a two-sphere, then it always has an unstable geodesic. So what you see on the round sphere, that there is an equator, an unstable geodesic, that holds for any metric at all on a two-sphere. Now, this is a special case of an old theorem which has been extensively studied by differential geometers, and I'll show you the proof in a minute. It was first stated by Markov in 1917. There's been a whole series of variations on it. Liston and Schneermann are two names associated with it, but there's various issues with the proof associated with questions about whether the geodesic that these arguments produced was really simple or not, whether it was an embedded geodesic. But anyway, there's a very simple argument now based on the curvature flow theory that was developed by Gage Hamilton and Grayson. So I'll show you that. Another property is that no region of the complement of this maximal family has four or more geodesic boundary components. So if you look at any of those regions, those surface regions bounded by that maximal family, you'll never see a piece with four boundary components. And there's a few other similar results. A region whose boundary is a single stable geodesic has to be a punctured torus. A region whose boundary is a single unstable geodesic has to be a disk. A region whose boundary has two geodesics has to be an annulus, and it has to have one stable and one unstable geodesic. And the region which has three boundary geodesics has to be a pair of pants whose boundary has three geodesics. So this is pure differential geometry, but it's very simple. Let me show you the arguments. It's sort of nice. So how do we see that any Riemannian metric on a two-sphere has to have some unstable geodesic, some embedded unstable geodesic? So let me show you this argument that goes back to Markov.
Excuse me.
Yes, question.
Is there a way to remember this long list?
Yeah, I'm going to go through them one at a time. And then I'll put it back up for you so you can remember it.
Yeah. I mean, what's the organizing principle?
Oh, what's the organizing principle? Well, there's either 1, 2, 3, or 4 boundary components. And you just check the cases for each one. That's, yeah, or more, 4 or more, I should say. But you just go systematically through each one. So let's say that there's a two-sphere. This is a region with 0 boundary components. How do we know that there always is an unstable geodesic, like the one that's drawn here? Well, what we do is we take a foliation, a family of curves that sweep out the two-sphere. So you can think of all the lines of latitude on a sphere. And the idea is to let them decrease in area all at the same time. Now, the original arguments that made this is, I think this is maybe one of Markov's one of the theorems Markov is known for, at least in Wikipedia. It's one of two theorems that they list for him. He didn't have curve flows, so he made an argument like this involving approximating these curves by polygons and flowing the vertices of a polygon and so on to shorten the polygon. But we today have this theory due to Grayson and Gage-Hamilton that says that there's a canonical way to shrink a curve by flowing by its curvature. And if you apply that to this family, you'll get a continuous family of shrinking curves. Now the curves near the point A0, you have this family A sub t is of curves as t goes from 0 to 1. The curves near the point A0 will shrink towards A0, and the curves near the points A1 will shrink towards A1. And somewhere in the middle, there'll be a curve that's sort of stuck. It doesn't know which side to flow to. And if you think about what happens to that curve, you can show that it flows to a geodesic. Okay, because the family stays continuous and as you flow, and each curve gets shorter with time. So there's some limiting curve there, which is a geodesic, and if you push it off to either side, you'll get shorter curves. One of the interesting theorems is that, in fact, you can always find at least three such curves, three distinct such curves. And one of the nice theorems that Morse proved was that on an ellipsoid, if you take an ellipsoid that's very close to a round sphere, there'll be exactly three. The three axes of the three symmetry planes will give you exactly all the simple geodesics on some ellipsoids. Okay, so let's look at 4 or more boundary points and show that these kinds of regions never appear in our maximal family. So you take any surface and take this maximal collection of separating geodesics, you'll never see a region with 4 boundary curves. And the reason is, just take 2 of those curves and tube them together, join them together in this way, and you get a new curve, right, which is not homotopic to any of the boundary curves. In fact, it's homotopic to the curve in the middle that splits those boundary curves. But every homotopy class of curves has a geodesic. So there's a geodesic somewhere here in the middle that's homotopic to the sum of those 2 boundary curves on the left. Do you want to see that again? I see a couple of suspicious faces there. Yeah. See, we took these 2 boundary curves and we formed a new homotopy class of curves just by joining them together like that, right? And that's a curve which is simple, and it's not homotopic to any of the 4 boundary curves. Well, so I said there was this basic theory that says that on a surface you can represent any homotopy class by a geodesic. So that curve has a representative by a geodesic. You might object to the fact that this is a surface with boundary, but as long as the boundary is geodesic, there's no problem in proving it for that case as well. So the shortest curve homotopic to this red curve must give you something that is separating, because each of the original curves was separating, so this curve is separating as well. And it wasn't in the original family, so the original family was not maximal, and we see that this kind of region doesn't occur. Yes?
Can the red curve touch one of the boundary components?
Right, so topologically it could, but geodesics have the property that if they touch in a tangent, then they're equal. They're determined by their tangent vector at one point. So it doesn't occur for geodesics. And the same is true for minimal surfaces. It's an important property that's used in this. Any other questions? Sorry. The question was, is it possible for this red geodesic that's produced in this way to touch one of the blue geodesics. And in fact, if the boundary components weren't geodesics, if they were arbitrary curves, then that could certainly happen. It could run along the boundary for a while, the shortest curve. But because they're geodesics, and geodesics are determined by first order differential equations, you can't have two of them touching and tangent. Any other questions? Yes?
Is there an argument for why this is never contractible that doesn't rely on like heavy fundamental loop machinery?
Of why the union of those two isn't contractible?
Yeah, because for a moment I was kind of confused. It looked a little bit like it might be, and it seems like
Right.
it shouldn't be, but I can't see an argument that doesn't rely on fundamental loop machinery.
Well, you could say, for example, that so the question was, is there a simple argument how you see that this red curve that we constructed doesn't contract to a point? And of course, you could compute it in the fundamental group, but there was a question of whether there's an easier way. I think there is. If you take the very top arc connecting the top left circle to the top right circle, so the arc connecting those two boundary curves, that crosses the red curve once, right? And the contractible curve has to cross anything twice. So you can sort of use its separation properties. The fact that it separates two of the boundary components shows that it can't be contractible. Okay, and I didn't cheat by drawing it like that. Even if I'd had some genus in there, the same argument would apply. You're getting a new homotopy class, and if you take the minimizer, you'll get a separating curve that was not in your family. Okay, so next case. What about if there's a single boundary component? So there's going to be two cases, if it's stable or unstable. So we'll first look at a single boundary component which is stable, meaning that, so we look at that red curve, and we assume that all nearby curves are longer, right? It's stable, so there aren't any nearby curves that are shorter. So that means when you push in, you must be getting longer. Now we have two possibilities. In the top possibility, we see the case where that red curve is the boundary of a disk. And then the Birkhoff Gage-Hamilton argument applies again. We get longer and then shorter. So we can run curve flow, and we get stuck on some blue curve in the middle, which is a geodesic. If it's not a disk, then it's got some topologies. So it could have genus more than one. It could bound the surface of genus more than one, or it could bound the surface of genus one. Now, if it bounded something of genus more than one, then we could separate those two handles by a curve and take the shortest curve in that homotopy class, and that would give us a separating geodesic, but we assumed that this region had no more. This is a region which has one of the original family on its boundary, and no more separating geodesics exist. None inside it. So we can't have genus more than one, or we wouldn't have had a maximal family. So the only possibility is that it must bound a...
Question about that last case.
Yes.
There's a homotopy class of curves going through the hole.
Yes.
Going around the right.
That's right.
Where did that go?
Right. So,
can this case
good question. So if you look back at, so I was hopefully careful to state this, and said G is a maximal family of disjoint separating geodesics. So I'm only looking at separating geodesics. The geodesic that goes through the hole is non-separating. There are many more geodesics on this torus, right? There's one that runs around like this, or like that, or many others, but each one of them is non-separating. So I have to throw that in for the surface. For the three manifold, when we're looking for three spheres, we can, as a first step, assume that the manifold is a homology three sphere, that everything is separating, because that's very easy to check computationally. But for surfaces, that would eliminate everything unless. So I'm adding this condition of separating to the curves. So what about a region which has an unstable geodesic, a single unstable geodesic? So this one, because it's unstable, we can push it off. We can push the boundary off a little bit and decrease the area. That's what being unstable means. But now we can keep on shrinking that curve until what happens? Either it shrinks to a point, in which case we have a disk, or it shrinks to some geodesic where it gets stuck. And in that case, we again don't have a maximal family. So the only thing that can happen is it bounds a disk if it's unstable. So that was case 4. What about a region with 2 boundary components? I claim it has to look like this. It has to have one unstable and one stable boundary. Question? Counterexample? So the argument is, supposing we had something with 2 boundary components that was not of this type. Maybe it has 2 stable or 2 unstable boundary components. So if it's got 2 stable boundary components, then when we so this left one, if it has 2 unstable boundary components, then we can push each one of them in, and each one of them will converge to some stable curve, which does not lie on the boundary. Maybe it's the same one if they co-bound an annulus, or maybe it's different ones, but in either case, our family was not maximal. And similarly, you can rule out the other case. You push in, and if those 2 boundary curves are homotopic, if they co-bound an annulus, then you get an unstable one separating geodesics inside.